Hello, my name is Harry Chen, and this is a lecture on Vieta's formulas. Vieta's formulas apply solely on polynomials, so we'll first go over what polynomials are. So a polynomial of degree n is represented by the expressions a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus on and on until we just get to a0 times x to the 0 if you want. So essentially, this is the sum from k to the equals 0 to n of a sub k times x to the kth power. It's important to note that if it's of degree n, then the leading coefficient, that is a sub n, cannot be equal to 0, because otherwise we could just reduce the degree down by 1. And so yeah, so this is essentially what a polynomial is. Yeah, and we'll be referring to polynomials using this kind of notation a lot in the when we use Vietas. Another quite important theorem that we have to go over is the fundamental theorem of algebra. So basically, this states that for any polynomial with complex coefficients with degree n, they all have exactly n roots in counting multiplicity. So if we have something like x cubed plus x squared plus 2x plus 1, we don't, well, equals 0, I guess. We already know by the fundamental theorem of algebra that there are exactly 3 values of x that work for this equation. So they can be complex, they can be real, yeah. And we know this because this has degree 3, because that's the highest power in this entire thing. Yeah. Now, I won't explain the proof of the fundamental theorem of algebra because it's quite advanced for what we're going to be doing. Yeah. So, but another thing to notice is that when we say counting multiplicity, we mean like if we have x squared plus 6x plus 9 is equal to 0. If we solve this by factoring, we get x plus 3 squared is equal to 0. So there only is one solution of x that works, and that's x equals -3. So, but we expect for there to be 2 solutions. So what's going on here? Well, the reason this doesn't violate the fundamental theorem of algebra is that this has multiplicity too. So notice how over here in the factor form we have a power of 2 here. Well, that's what that means, as a multiplicity of 2, and so we say that x equals 3 is a solution, but x equals 3 is also the second solution. So yeah. Now that we know what the fundamental theorem of algebra is, we can apply it to the Vieta's formulas, or we can introduce the Vieta's formulas. So basically, Vieta's formula goes like this, on quadratic at least. Let the roots of the polynomial ax squared plus bx plus c be p and q. So notice how there are exactly 2 roots given here, which matches the fundamental theorem of algebra saying that there's, this has degree 2. Yeah, so let the roots be p and q. Then p plus q is equal to minus b over a, and p times q is equal to c over a. So the proof of this is it's quite basic. So for any polynomial, we can factor it like this. So it'd be x minus p, a times x minus p times x minus q. And we set this, yeah, so a times x minus p times x minus q. We know that p and q are going to be zeros, or roots of this function, because if we plug it in, it makes one or both of these equal to 0, which makes the entire thing equal to 0. And so we know that this is equivalent to the polynomial we put in the formula here. So this has to be equal to ax squared plus bx plus c. However, if we expand this out, we get ax squared minus a p plus qx plus a times pq. And so if we match coefficients, so we know that ax squared has to equal ax squared, which is all obvious. But we also know that a times p plus q, or sorry, negative a times p plus q has to equal b. And then a p q has to equal c. If we divide minus a from both sides here, we get p plus q is equal to b over minus a, and if we divide a from both sides here, we get pq is equal to c over a, which is exactly what the theorem states. Let's try this on some examples. So, problem 2.2 or example 1. Given that alpha and beta are the roots of 3x squared minus 50x plus 63 is equal to 0, compute alpha plus beta and alpha times beta. So alpha plus beta, if we just apply the Vieta's formula directly, we get that it's equal to 50 over 3. Because the negative here cancels out with the negative in the formula. And then alpha times beta is equal to 63 over 3, which is equal to 21. So yeah, that's a pretty quick application of Vieta's. This is another problem that uses Vieta's. So it looks very similar. We have the exact same polynomial here, 3x squared minus 50x plus 63. But this time it just wants us to compute 1 over alpha plus 1 over beta. So to do this, let's combine denominators here. So this is equal, if we multiply the top and bottom of this by beta and the top and bottom of this by alpha, we can get that this is really equal to alpha plus beta over alpha times beta. Well, we already calculated what these two are equal to, so we know that the top is equal to 50 over 3, and the bottom is equal to 21, and so in all this is equal to 50 over 63. Yeah. Also notice that this is equal to negative b over a. Oh, sorry, negative b over c. That's kind of interesting. It works for all quadratics. You can prove it yourself, I guess, if you want. Yeah. So 50 over 63 is our answer for this one. So notice how cool this was. It gave us this weird, complicated expression. It wasn't that complicated, but it was weird at the very least. And without even having to find alpha or beta, we were able to pretty easily and pretty quickly compute what this was. And that's kind of where the power of Vieta's formula lie. It allows us to compute really weird stuff with relative ease. So that was Vieta's formulas on quadratics. But Vieta's formulas are more powerful than that. It can be applied to cubics, quartics, quintics. It really can be applied to any polynomial. And so this is the Vieta's formulas generalized. As a side note, there was a section cut out from this lecture for the sake of timing, but there is a section slightly before this on the handout that will be listed in the description. Please give that a look if you want some more detailed analysis of this. So anyway, the Vieta's formula is generalized. Let the roots of the polynomial a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way up to a sub 0, and let the roots of that be x1, x2, x3, x4, all the way up to xn. Then the symmetric sum of x1, x2, all the way up to xk is equal to -1 to the power of k times a sub n minus k over a sub n. So it's kind of a complicated formula. Well, let's first break down what the symmetric sum really means. So the symmetric sum basically, if we have symmetric sum basically wants us to list out all permutations of x1, x2, xn. So if we do all combinations of this, not permutations, combinations. I don't know what, depending on the size. So if we have size 3, then all permutations of this would be like x1, x2, x3, plus x1, x2, x4. Whoops. Plus x1, x2, x5. Let's just say that n is equal to 5. So I'll scratch this out. We'll do 5. And then yeah, so and then we do plus x2, x3, x. Wait, that's not right. x1, x3, x4 plus x1, x3, x5 plus x1, x4, x5 plus x2, x3, x4. I hope you get the point. So basically, when n is equal to 5 and k is equal to 3, we go through all 5 choose 3 possibilities for these terms, and we just kind of loop through them and then sum them all together. Yeah, so 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5, 2, 3, 4. Those are all different permutations of 1, 2, 3, 4, 5 of size 3. And so we just add all those together. And then, of course, this is going to be equal to plus dot dot dot. This is going to be equal to negative 1 to the k times a n minus k over an. And the proof of this is very similar to the proof of the Vieta's formula for quadratics, as in we basically use the factored form. So like an times x minus x1 times x minus x2 all the way up to x minus xn, and then we just expand that out and equate all the powers. So and we equate all the coefficients. So the x to the n minus 1, the coefficient of that has to be equal to the coefficient of x to the n minus 1 of the other version of the polynomial. And so that's how we come up with all these formulas. It's quite intuitive, actually. But of course, yeah, the proof of that will be discussed in the handout. I don't want to go into too much detail here because there's a lot of written work. So when we write it out using x1, x2, x3, it can get a little bit confusing. So let's see a practical example. The roots of the polynomial 2x to the 5th plus 15x to the 4th plus 10x cubed plus 26x squared plus 50x minus 1 be a, comma b, comma c, comma d, comma e. Compute abc plus abd plus abe plus acd plus ace plus ade plus bcd plus bce plus bde plus cde. Well, that was a mouthful. Yeah, so if you notice that all of this is just every single permutation of size 3, of length 3, of A, B, C, D, E. So there's yeah. And so that means we can use Vieta's formula quite well on it. So here's how we'll do it. So this is equal to the symmetric sum of ABC, so of size 3. And so we know that this is equal to, I'll write sim here. Since it's of size 3, it's equal to negative 1 to the power of 3 times a5 minus 3 over a5. The 5 here comes from, of course, the fact that this is of degree 5. Oops. So yeah. So all this would be equal to negative a2 over a5. That looks like a 3. Let's fix that. And so a2 is this, and a5 is this. So this is equal to negative 26 over 2, which is equal to minus 13. So yeah, that was quite easy, and it was a lot cleaner than, finding each individual root and then bashing all of that. So yeah, that was pretty nice. Yeah. If you want a slightly easier way of thinking about it, we can think about like each time the size of this increases, we go left 1, and then we also make it negative. Yeah. So this would be negative here, positive here, negative here, positive here, negative here. Yeah, so we would alternate there as we go right. But yeah, and the answer is negative 13. So that was quite nice. Here's another practical example of it. Let the roots of the polynomial 2x cubed minus 6x squared plus 10x plus 16 be a, b, c. Compute a cubed plus b cubed plus c cubed. So unfortunately, a cubed plus b cubed plus c cubed doesn't really look like any of the Vieta's formulas directly, but yeah, it doesn't look like any of it directly. But let's try to turn this into something that we can use Vieta's formulas on. So using Vieta's formulas, what do we know? We know that a times b times c, that's going to be equal to negative 16 over 2, so that's going to be equal to 8, right? We know that AB plus BC plus CA is going to be equal to, let's make that look a little bit better. AB plus BC plus CA is going to be equal to 5. And then we also know that A plus B plus C is going to be equal to 3. So these are the things we know. We know ABC, we know AB plus BC plus CA, and we know A plus B plus C. We want A cubed plus B cubed plus C cubed. So let's take this equation here and let's cube both sides. So we get A cubed plus B cubed plus C cubed plus I think it was 2AB plus BC plus CA plus this is right. Wait, I'm sorry, no, it should be a little bit more than that. Oh, and I see the issue. Sorry. So A cubed plus B cubed plus C cubed plus 3 times A squared B plus AB squared plus B squared C plus BC squared plus A squared C plus AC squared plus 6ABC. And then we know that this is equal to 3 squared, which is 27. So if we notice, we have an A cubed plus B cubed plus C cubed here, which is nice. And we also have a 6ABC here, which is also pretty nice because we know what that is equal to. That's equal to 8. So we just need to simplify this middle term here. How do we do that? So we can try multiplying this formula here with this formula here. So we get that if we do that, if we multiply these two together, we get A squared B plus AB squared plus B squared C plus BC squared plus A squared C plus AC squared plus I think 3ABC is equal to this would be equal to 15. Whoops. Yep. And yeah, so that means we can rearrange this to get that, this whole thing here is equal to 15 minus 3ABC. So we're almost done here. Let's put this together. We can substitute this weird horrific thing into the first equation to get that A cubed plus B cubed plus C cubed plus 75, well, not 75, 45 minus 3ABC equal to 27. And so that would mean that A cubed plus B cubed plus C cubed is equal to it's an equal to negative 8, sorry. And so we know this would be equal to, let me calculate for a second, negative 42. That is our final answer. Yep, so again, this is a lot easier than finding the roots. Yeah, really, I'm not sure if it would be possible to find the roots in this case, probably be very hard, but Anyway, minus 42 is the answer here, and yeah. And so, yeah, a lot of times Vietas will also come down to just a lot of factoring or a lot of like manipulation or rearranging. So make sure you have your algebra bone out for that. Yeah. So the previous problems we did were more traditional, I guess not traditional, but they were more straightforward usages of Vieta's formulas. Typically problems won't be like that. Generally Vieta's formulas are used as an intermediate step of a problem instead of the main focus of it. So here's such a problem, USMCA 2020 Challenger number 12. Yeah. So this was an online competition that was held this year. Let a, b, c, d be the roots of a quartic polynomial f of x equals x to the fourth power plus 2x plus 4. Find the value of this whole thing. So a squared over a cubed plus 2 repeated 4 times, basically. So before we touch this at all, we kind of want to simplify a squared plus a cubed plus 2, because that's kind of, it's very unwieldy to work with. And so to simplify this, let's note on the side here, we can use the f of x is equal to x to the fourth plus 2x plus 4. If we just rearrange this, we get that, well, first of all, notice that if we plug in a, b, c, or d into this, since the roots, by definition, it's going to be equal to 0. So we can do some rearranging. So to find that x cubed plus 2 is equal to negative 4 over x. And we did that by subtracting 4 and then dividing both sides by x. And so we can substitute that in here to get that this is equal to a cubed over 4, the negative of that. And then we can simplify this further, because this is still a little, we can technically do this, we can technically solve the problem like this, but you know, we can technically solve the problem like this. I mean, because you can kind of look in the problem we just did to see why, but this is still kind of bad to work with. So preferably we want to simplify this a little bit further, and we can do that. If we rearrange this a little bit further, we see that x cubed is equal to minus 4 over x minus 2. So really this is going to be equal to so 1/4 of 4 over x plus 2, right? And so this is just equal to 1 over x plus 1/2. Oh, sorry, 1 over a. These should both be a's. Yeah, that's close enough. 1 over a plus 1 over 2. And so that simplifies it greatly. We can apply the same logic on the b and the c and the d one. And so what we really need to solve is we need to solve 1 over a plus 1 over b plus 1 over c plus 1 over d plus 2. So if you remember the 1 over alpha plus 1 over beta problem, let's try combining denominators. So this turns into ABC times, plus BCD plus CDA plus DAB all over ABCD plus 2. And then we can use Vieta's formula on the top and bottom, right? Because we know, from Vieta's formula, we know what these are equal to. And so we get this is equal to minus 2 over 4 plus 2. And so that's just equal to 3/2. And we're done. Simple, and that was pretty simple. Yeah, so just if we step back, really we only used Vieta's formula like once in this entire problem. The rest of the problem we just did a bunch of polynomial rearranging. We just did a polynomial rearranging. Yeah, so Vieta's was very helpful though. It really helped simplify 1 over a plus 1 over b plus 1 over c plus 1 over d. So don't discount it either. So if you remember back to the problem that wanted a cubed plus b cubed plus c cubed, Well, you may have noticed that it was a pain to do. It took a long time. And it's really not that hard once you see the trick. And furthermore, well, it doesn't extend nicely. If it wanted a to the fourth power plus b to the fourth power plus c to the fourth power, it would take a bunch more work. So to combat this, we have something called Newton sums. I don't know if it was Newton who made these or if it was just named after him, but either way, they exist. So it goes as follows. Let the roots of the polynomial a sub n times x to the n, you get the story, be x1, x2, all the way up to xn, and let p sub k equal x1 to the kth power plus x2 to the kth power plus dot 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 plus x to n to the kth power, where k is a positive integer. So basically just the sum of the power of x's to the kth, sum of x to the kth power. Then the following holds where if we let a sub n equals 0 whenever m is less than 0. So basically the coefficients of all the negative terms is 0 for obvious reasons. Okay, so basically it gives us the system of equations. 0 is equal to 1 times a sub n minus 1 plus p sub 1 times a sub n. 0 is equal to 2 times a sub n minus 2 plus p1 times a sub n minus 1 plus p2 times a sub n. And then it keeps on going in a similar fashion. Yeah. And okay, so this looks complicated, but really when in practice, it just comes down to solving a bunch of linear equations in a row. Because you basically start at you start at this first equation up here, and then you can solve for P1, and then you use that in this equation to solve for P2, and use that to solve for P3, on and on and on. So, and then you just stop whenever you find the correct power of P. So, it isn't as bad as it looks. It's just, the main issue is that it's just kind of hard to remember and it's a little bit clunky. Yeah, so let's use it on the problem from before. Let the roots of the polynomial 2x cubed minus 6x squared plus 10x plus 16 be ABC. Compute a cubed plus b cubed plus c cubed. So, yeah, so the first equation that we got to solve is 0 is equal to a sub n minus 1 plus p1 times a sub n. Oh yeah, yeah, by the way, the thing this is equal to, this is just p3. If we can find p3, then we're done with the problem essentially. And so, okay, so we know what a n minus 1 is. This is a n minus 1, this is a n, so 0 is equal to minus 6 plus 2p1, which means p1 is equal to 3. Okay, so the next equation is 0 is equal to 2an minus 2 plus p1 an minus 1 plus p2 an, yeah. So this is equal to 0 is equal to 20 plus, so p1 is equal to 3, a times n minus 1 is equal to negative 6, so this is negative 18 plus 2p2. And so this means that p2 is equal to negative 1. Okay, and then our third Newton sum equation is 0 is equal to 3 a sub n minus 3 plus p1 a sub n minus 2 plus p2 a sub n minus 1 plus p3 a sub n. Okay, and then we can substitute this in again to get 48 plus, so 3 times 10, that's 30, plus negative 1 times negative 6, that's 6, plus 2p3. So this means that 84, sorry, 84, or negative 84 is equal to 2p3, which means that we have that p3 is equal to negative 42, which is exactly what we saw when we did all the factoring stuff. So yeah, Newton sums works. It's just a little bit bashy. It's a little bit less bashy at least than manually computing it. So anyways, that'll be the end of this lecture. If you want to dig a little bit deeper, take a look at the handout that is linked in the description. And thanks for watching. Watch some of our other videos if you want.